In this video, we're going to talk about sequences. A sequence in mathematics is defined as a function whose domain is the set of positive integers. We often represent sequences by subscript notation. The first item in the sequence would be a sub 1, the second would be a sub 2, all the way down to the nth term, which would be a sub n. And if you wanted to think of this as a function, you would say f of 1 equals a sub 1, f of 2 equals a sub 2, and f of n equals a sub n. The terms a1 through an are called the terms of the sequence, and the number a sub n is called the nth term of the sequence. Sometimes we start a sequence with a sub 0, and the domain is a set of non-negative integers 0, 1, 2, 3, all the way to infinity. Sometimes we start with 1. It just depends on the context. These examples say to list the first 5 terms of each sequence. So here we have a sub n, the nth term, is equal to 2 plus negative 1 to the nth power. So a sub 1, we're just going to plug in 1 for n, will be 2 plus negative 1 to the first power, which is 2 plus negative 1, or 1. A sub 2 will be 2 plus negative 1 squared, which is 2 plus 1, or 3. A sub 3 will be 2 plus negative 1 to the third power, or 2 minus 1, which is 1. A sub 4 will be 2 plus negative 1 to the fourth power, which is 2 plus 1, or 3. And a sub 5 will be 2 plus negative 1 to the fifth power, which is 2 plus negative 1, or 1. Make sure you're paying attention to your instructions. If it doesn't tell you to start with 0, you can assume you're going 1 through 5. Just make sure you're following what it tells you to do. This one's defined in terms of b, and we have n divided by 4 minus 2n. So b sub 1 will be 1 divided by 4 minus 2 times 1. So that gives me 1/2. B sub 2 would be 2, because it's n. So we'd have 2 divided by 4 minus 2 times 2, which gives me 2 over 0. That means that the second term here is technically undefined. B sub 3 would be 3 divided by 4 minus 2 times 3, so that's going to be 3 divided by 4 minus 6, so negative 2, or negative 3/2. B sub 4 will be 4 divided by 4 minus 2 times 4, so that gives me 4 over negative 4, or negative 1. And then finally, b sub 5 will be 5 divided by 4 minus 2 times 5, so that gives me 5 over negative 6, or negative 5/6. For the last example, we have c sub n equals n divided by 2 to the nth plus 1. So c sub 1 would be 1 over 2 to the first power plus 1, so 1/3. C sub 2 would be 2 over 2 squared plus 1, so that's 2/5. C sub 3 would be 3 divided by 2 cubed plus 1, so that's 3/9, or 1/3. C sub 4 would be 4 divided by 2 to the fourth plus 1, so that gives me 4 over 17. And C sub 5 would be 5 divided by 2 to the fifth plus 1, so that's going to be 5 over 33. And you may see these also just listed in curly braces with commas between them. That's okay also. A special class of sequences are recursively defined sequences. Sometimes we give those a, b, and c. Sometimes we give them a subscript like d sub n. This defines each new term of the sequence as a function of one or more of the previous terms. So one of the classic examples of this is what we call the Fibonacci sequence, and you may have seen this on another topic. I remember it was the subject of one of the old MathNet videos, if you ever pull those out of the closet where they're collecting dust. They're kind of cute. But the idea is that a sub n plus 2 is equal to a sub n plus 1 plus a sub n. Each new term is equal to the sum of the previous two terms, and you start with the base case that says a sub 1 equals 1 and a sub 2 equals 1. So when you go to list out your sequence, you'd have 1, 1. You'd add those two together and get 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, so on and so forth. So that's a classic recursively defined sequence. You just add the previous two terms. You do have to know a starting point. That's very important. If you don't have a base case, you can't find the value of a recursively defined sequence because you don't have anything to base it on. So this one says list the first 5 terms of d sub n where d1 equals 13 and d sub n plus 1 equals 2 times d sub n plus 1. So d sub 1 is going to be 13. D sub 2 is going to be 2 times d sub 1 plus 1. If this one is n plus 1. So if this one is 1, this one is 1 plus 1. So that gives me 2 times 13 plus 1, because I just plugged the previous number in, which gives me 27. D sub 3 will be 2 times d sub 2 plus 1. So we'll take that 27 and plug it in, and we get 55. D sub 4 will be 2 times d sub 3 plus 1. So that's 2 times 55 plus 1, which gives me 111. And d sub 5 will be 2 times d sub 4 plus 1, which gives me 2 times 111 plus 1, or 223. So those would be my first 5 terms. Any sequence whose terms approach limiting values is said to converge. So this is an example of a sequence that converges. It's written as the terms 1/2, 1/4, 1/8, 1/16, and 1 over 32. And if you look closely at it, you can see that a sub n, the nth term here, is 1 over 2 to the nth power. It's increasing powers of 2. And as n approaches infinity, as n gets larger and larger and larger, this whole fraction is getting smaller and smaller and smaller to the point where this particular sequence is going to converge to 0. So if L is a real number, the limit of the sequence a sub n is L is written as the limit as n approaches infinity of a sub n equals L. If for each epsilon greater than 0, there exists an m greater than 0 such that the absolute value of a sub n minus L is less than epsilon whenever n is greater than m. This should look kind of familiar to you. If the limit L of a sequence exists, then the sequence converges to L, but if it does not exist, then the sequence diverges. So this is the theorem called limit of a sequence, theorem 9.1. If we let L be a real number and let f be a function of a real variable such that the limit as x approaches infinity of f of x equals L, so this is a real valued function, meaning you can plug any real number into it, then the sequence where the each nth term can be found by plugging n into that function f is also is going to have the limit L. Just like with functions, sequences can fail to have a limit if they increase or decrease without bound, or if they alternate between two values. Some properties of the limits of sequences. These should look very familiar to you. If you are adding two sequences or subtracting them, you can subtract or add their limits if they exist. You can multiply by a constant. You can multiply two limits together and divide as long as the denominator is not 0. So these examples say to determine whether or not the following sequences converge, and if they do, find the limit or write diverges. So basically what we're going to do is we're going to find out if the limit as x approaches infinity exists, then what would happen, can we take the limit as n approaches infinity of this particular sequence. So I'm going to say the limit as n approaches infinity of 2n over n minus 1. And of course, if you were to plug an infinitely large number into the numerator and the denominator, you would get infinity over infinity. So that gives us the indeterminate form infinity over infinity. And to deal with that, we need to use L'Hopital's rule, which says that we can take the derivative of the numerator and the denominator. So we'll have the limit as n approaches infinity of 2 divided by 1, which is just the number 2. So we can say that the sequence a sub n converges to 2. For this one right here, we would be taking the limit as n approaches infinity of 4 plus n. And if you take infinity and add 4 to it, you just get a slightly bigger infinity. So this one we definitely would say diverges. It doesn't converge to a single value. This one is interesting. Here we've got a sub n equals 5 minus negative 1 to the nth power. So as n approaches infinity, what happens to this negative 1 to the nth power? It's kind of hard to say because, I mean, depending on what you plug into that power, it could be even or odd. It could make that number positive or negative. So you might want to look at some terms. So I might look at a sub 1, which would be 5 minus negative 1 to the first power, or 6. A sub 2 would be 5 minus negative 1 squared, so that's 5 minus 1, or 4. A sub 3 would be 5 minus negative 1 cubed, which is 6. And then a sub 4 would be 5 minus negative 1 to the fourth, which is 4. So you can see what happens. This thing is oscillating between two values, so we say that a sub n diverges. Now you do want to be careful and don't just assume that anytime you have negative 1 to the n, it's going to oscillate between two values and converge, and diverge. Because, for example, if you had something like this one, negative 1 to the nth power over n, if you take the limit as n approaches infinity of this thing, what you end up getting is 0. So if you were to graph out the real function, or even just the points, as n approaches 1, as n equals 1, 2, 3, 4, 5, so on and so forth, you end up with something that kind of looks like this. So at 1, we would have negative 1 over 1, so that's negative 1. At 2, we would have positive 1/2. At 3, we would have negative 1/3, and so on and so forth. So you can see that it is approaching the number 0. It's just kind of doing this back and forth motion to get there. But that limit still exists. So we would say that this one converges to 0. And like we saw a minute ago, sometimes we do need L'Hopital's rule. So the limit, for example, as n approaches infinity of n cubed divided by e to the 3n, I'm going to use L'Hopital's rule because this would give me infinity and this would give me infinity. So this would be the limit as n approaches infinity of 3n squared divided by 3 e to the 3n. Again, I get infinity over infinity, so we'll use L'Hopital's rule again. So I would get 6n over 9 e to the 3n. And again, we have infinity over infinity, so I would use L'Hopital's rule again. And I would get 6 over 27 e to the 3n. So now we have a fixed constant divided by something that's approaching infinity. So this one is 0, so we can say that this one converges to 0. And the last topic I want to talk about in this video is factorials. So you've probably seen these before. They occur a lot in statistics and probability. They occur a lot in combinatorics, if you're interested in the study of counting things. They also occur a lot in sequences and series, so we'll play with these a lot throughout this chapter. This symbol right here, n with an exclamation point, is read n factorial, and it's defined as the product of all of the positive integers from 1 through n. So for example, something like 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, and whatever that integer is when you multiply all those together. This is a recursive definition. The 0 factorial is a special case defined as 0 factorial equals 1. So for example, n factorial, when I say it's recursive, you could think of it as n times n minus 1 factorial, or n times n minus 1 times n minus 2 factorial, or you could just keep taking off the top part of that stack and going down to the next number. So let's evaluate some of these. 1 factorial, of course, would be 1. 2 factorial would be 2 times 1, or 2. 4 factorial would be 4 times 3 times 2 times 1, which is 12 times 2, or 24. And you can just keep counting, so on and so forth. So 5 factorial, if it asked for that, would be 5 times 4 factorial, which is 5 times 24, or 120. Factorials follow the same conventions of order of operations as exponents do. So if you have something like 3n factorial, only the thing directly in front of the exclamation point is having the factorial taken from it, unless you have parentheses. So 3n factorial is the same thing as 3 times n factorial, which would be 3 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1, or however big this n happens to be. Whereas 3n factorial would be 3n times 3n minus 1 times 3n minus 2, all the way down to 3 times 2 times 1. So you can see the difference between the two. In this one, the 3 is not included in the factorial, but in this one, because of the parentheses, it is. You may have to do some simplification with factorials. So for example, if you're asked to simplify something like 4 factorial, 3 factorial over 6 factorial, what I would do is I would start with the highest number, and I would count down to the next highest number. So this 6 factorial, I want to try to cancel with the 4 factorial. So I'm going to count down 6 times 5 times 4 factorial. Just keep taking off the next item on the top of the stack until you get down to 4. And then I'm going to remember that 3 factorial is actually 3 times 2 times 1. That's not too hard to work with. So now I can cancel the 4 factorials. And you do have to cancel the entire factorial. I get 6 over 6 times 5, which is 1/5. If I had no numbers, perhaps I had something like n minus 1 factorial over n times n minus 2 factorial. Something like this. This should be an n minus 2 factorial. What I could do is I could take, now notice that the n is not factorialed here, so you don't want to start with that one. You want to start with n minus 1 factorial. And if I were to subtract 1 from that, the next thing would be n minus 2 factorial. So I can cancel these two, and I'm left with n minus 1 over n. So you might want to review simplifying factorials, because you are going to see this from time to time as you go about working through the rest of this chapter.